Here is Joe Fish from Boston, and he will talk about feral curves and minimal sets.
All right, so my mic's on? All right, sounds like it is. Good. So thank you very much, and thank you for the invitation to speak here. First time in Rio, so this is fantastic. Right, so I'll be talking about feral curves and minimal sets, and this is joint work with Helmut Hofer. I want to point out that the paper is now in the archive, so if I make any mistakes, you can check my work there. Yeah, I guess we can get started. So let's see. So let's start with a conjecture, and this is due to Gottschalk in the 1950s. I think about 1958. In dynamical systems, which says the following: does there exist a smooth vector field on S3 whose flow is minimal? So I think he posed it more as a question than a conjecture. And maybe I could just sort of remind, I guess you're very familiar with dynamical systems. Minimal is sort of a standard sort of gadget, but maybe if you're coming from pseudo-holomorphic curves, less so. So a flow on a manifold is said to be minimal if every trajectory is dense. Right? So in particular, if you have a flow on a manifold and you have a periodic orbit, that periodic orbit's not going to be dense, and so consequently it can't be minimal. And in particular, then, your flow can't have any closed invariant subsets at all of any type. No invariant tori, no interesting Cantor sets, et cetera. Good, so Gottschalk sort of said, okay, maybe is it the case that there's such a flow on S3 which is minimal, every trajectory is dense. And so this conjecture was made, and it's a really interesting conjecture, and not that much progress has been made on it directly. There's been some variants where people made interesting progress on it. But this specific one, I would say very little progress has been made, and none was made for a good, I guess, 40 years. And so then a question was posed.
So conjecture does exist or it does not?
As historically, right? I don't. Every time I say it, I think that if you had asked him, he would have said that such a flow does not exist. But it seems to be the case that when it's quoted, people sort of quote the reverse. I think it's a little bit like the Seifert conjecture, right? Sort of the author of the question sort of really thought one thing, but everyone quotes the reverse, so they can say they disproved something. So this question then came from Michel Herman in the 1998 ICM. And he said, and this was motivated by the Gottschalk conjecture and the lack of progress, I think. When n is bigger than or equal to 2, can one find a compact, let's see, a C infinity, compact, connected, embedded hypersurface in R2n whose characteristic flow is minimal. Characteristic flow is just a Hamiltonian flow for suitable Hamiltonian for which your hypersurface is a regular energy level. And so theorem, and this is the main thing that I want to talk about today, and this is with myself and Helmut, is the following. when n equals 2, no. That is, every regular, non-empty energy level of a smooth, proper Hamiltonian has a non-trivial closed invariant subset. Well, I guess as I'm erasing it, I suppose. So the idea here is that, so the Gottschalk conjecture, which I've now sort of partially erased, is this question just about flows on S3 in general. Not a lot of progress was made, and so Michel and Mons kind of changed the problem a little bit and sort of said, okay, how about if we loosen it up so it's not S3, it can be lots of different types of manifolds, but in particular, we're looking at sort of Hamiltonian flows on just on energy levels in R2n. And again, sort of the problem sort of floated around for a while, and then this answers the question in the negative in sort of this two-dimensional case. So a lot of what I'll say today, so let's see. To prove this, we have to build up a lot of techniques using pseudo-holomorphic curve methods, and all of those pseudo-holomorphic curve methods are going to carry over into higher dimensions. So anything I say specifically about pseudo-holomorphic curves today, and that we did in the paper, carries over into higher dimensions, which seems very promising. However, we can only do the n equals 2 case because 2 plus 2 is 4, right? Because we have intersection theory in dimension 4 for pseudo-holomorphic curves. We don't have that in higher dimensions. Okay, so that means I need to talk a little bit about pseudo-holomorphic curves. And a lot of this I can just go over very briefly because Richard provided a lot of the details that I needed already. But maybe just to establish some notation. So this, maybe you have a 2n-dimensional manifold, and J is going to be my almost complex structure. Right, satisfies this condition here in pseudo-holomorphic curves. Right, these are maps from from a Riemann surface into an almost complex manifold with a property that the tangent map intertwines the almost complex structure on domain and target. Right? And again, much like Richard, I'm going to be ambiguous about whether or not I'm going to call this a pseudo-holomorphic curve or a pseudo-holomorphic map. It only becomes important really when you start to write down details, and so I want to give you some ideas of what's going on, so I don't want to worry about that detail too much right now. Related, we also have a 2n, say, plus 1 dimensional manifold, or minus 1, it doesn't matter so much. I'm going to put a framed Hamiltonian structure on it, which I write a little bit different than Richard. I'm going to write it as eta equals this pair lambda omega. And so my lambda and Richard's lambda are the same, and my omega and Richard's omega are the same. The only difference is he had this, let's see, so what this means then is that lambda wedge omega to the n is a volume form, and d omega is 0. And these are the only two conditions that I'm going to place on it. So if you're familiar with pseudo-holomorphic curves in these cases, there's usually a stability condition, which now I don't want to assume. We'll see what problems, that sort of causes all problems later, but then it's also what makes the result interesting. Good. Any questions so far? Yeah?
Like
Pardon? It's not clear to me. I don't know. Yeah. The Gottschalks or Marcelo or this was Ginsburg and Nietzsche proved this for non-uniquely ergodic, I think.
So that cannot. So this is like. Is there something which is?
Oh, analogous for. Victor, do you know?
Well, I don't know any exact example. Those examples of, as far as I understand, all the examples of what is observed, minimal but not uniquely ergodic flows are.
I see. Okay.
So there should be some homology.
I see. Okay. Fair enough. Yeah, I mean, asking around sort of a little bit, I think that in some sense a natural class of objects to study from a dynamical systems perspective is ergodicity or unique ergodicity, for instance. I mean, a very sort of measure theoretic approach. And this minimality question just doesn't seem well adapted to the techniques from dynamical systems in general, I think, right? So people maybe sort of moved away from it because it was kind of not the right question to ask with, you know, the tools that were natural, I think. So I think, so that might also contribute to sort of the dormancy of its problem for a while. So back here, so I want to call this a framed Hamiltonian manifold. And then you can also then talk about the corresponding, let's see, oh, maybe I should give just an example. Well, just an example of these. They're, at this level, without sort of the stability condition, they show up pretty much anywhere, right? The idea is you say, well, how about if I take a symplectic manifold, so this is a symplectic form, put on an almost complex structure which is compatible, and that guarantees a Riemannian metric. Right, and then suppose you also consider a map H from W into R, and suppose 0 is a regular value, so you can define a manifold M to be H inverse of 0, and you have this inclusion map then from M into W. No, it's a stability condition on the pair lambda and omega. The condition that gets removed is that let's see. I think we need that that d lambda restricted to the kernel of omega is 0. That's the condition that gets removed. So maybe I'll just cross it out. There. Right, and so in this case, you can then define lambda and omega. So omega is easier, we see. We just look at the pullback of capital omega. And then lambda is, let's do d, h, compose j, and then I star this with a minus sign. Right. And this gives a framed Hamiltonian structure. You might want to normalize this if you so choose, if you want the Hamiltonian, the Hamiltonian vector field the regular way you would write it down to match up with the one that you get from this pair, but that's fine. The result of this then, let's see, the result of these conditions here guarantee the existence of, Richard called it a Ray vector field. I don't know, I prefer to call it a Hamiltonian vector field, which is determined by the following equations. Right? So we now have lots of examples. Basically, any energy level of a generic energy level, regular energy level, sorry, of a Hamiltonian, gives rise to a framed Hamiltonian manifold or structure. Good. So then we can talk about, I'll put it in quotes, the symplectization, which for me really just means we have R cross M together with this almost complex structure, which is translation invariant and satisfies basically all the properties that Richard said yesterday. So put a coordinate on R, and then we just want the symplectization direction when we apply J to that to get the ray or the Hamiltonian vector field. And then we have similar conditions on J mapping, keeping invariant the equivalent of the contact structure. I guess I should say, for the contact people in the audience, that this condition here also guarantees that the flow of your vector field, of your ray vector field or Hamiltonian vector field, preserves the kernel of lambda. And since we removed this condition, that's no longer the case anymore. So you really have total freedom to choose lambda. It sort of plays very little role, somewhat strangely. Okay. Good. When we fix this almost complex structure here, we also get a metric for free given by dA squared plus lambda squared plus omega semicomposed J. Right? And the benefit of this metric, for me at least, is that it's a translation invariant metric, right? So now we have a metric in an almost complex structure, it's an isometry, and that's kind of the region I like to play with pseudo-holomorphic curves in general. So I tend to focus on metric properties than symplectic properties. So let's make a couple of observations. None of these are sort of deep. But suppose it's the case that you have a pseudo-holomorphic curve right? Suppose you have a pseudo-holomorphic curve here, then what you can do is you can look at the integral of u star dA wedge lambda plus omega over sigma, and it turns out that this is actually equal to the area with respect to the pullback metric of sigma. So this is sort of simple enough. And then, I want to put this, I'll move down over here. As a consequence, I can talk a little bit about the notion of energy. So this formulation is different than probably anything, well, of most definitions that show up, although Taubes uses this one, so I'm not going to be the only one. So I'm not a huge fan of just writing a bunch of symbols down and expecting people to decipher them. So let me draw a picture to explain what's going on here. Right, you have some pseudo-holomorphic curve, you know, who knows what it looks like. And over here you've got some sort of symplectization, in quotes, of a frame Hamiltonian. You have some pseudo-holomorphic map. And then you look at the image. Right? So you have some image of a pseudo-holomorphic curve, and then what I've tried to draw on here is that you look at this sort of thickened, you look at a thickened symplectization slice, if you like. So this level here is A naught, and this level here is A naught plus 1. And so you make this sort of thickened window, and then we compute this integral, but we said that this integral computes the area with respect to the pullback metric. Or as long as your curve isn't sort of multiply covered in some sense, it computes the area of the image. And so you compute that area, and then you take the supremum over all possible shifts of where you're sort of looking at that window. And that gives rise to an energy. And this is equivalent to the Hofer energy if you're looking at pseudo-holomorphic curves and symplectizations of contact manifolds or stable Hamiltonian. So it's equivalent in that case, but we needed something sort of slightly different in the framed Hamiltonian case. Good. Good, okay. So how then do we prove the main result? So the setup, once you do, like these are sort of, this stuff here is all kind of minor adaptations of stuff that's all well known and well thought out. And so, we adapt another idea, basically right from Helmut's 93 paper. And so the idea is this. So let me say, yeah. So here's R4, right? And now we want to look at some sort of an energy surface in here. And if you're looking, one thing that I think is really important to stress is that this energy surface can just look like anything. So one of my favorites is to sort of take the round sphere, take a slightly shrunken round sphere, and then take a connect sum between the two, right? It's definitely not contact type. It's really weird. It effectively looks like positive tight S3 connect sum negative tight S3, sort of roughly. But nevertheless, our results hold in this case, even though it's not contact at all. And the idea then is to say, okay, we then have this inclusion into CP2, so maybe here's CP1 at infinity, right? And if this right here is supposed to be H inverse 0, then that gets mapped to sort of something over here, H inverse of 0, right? Good, and then the idea is to say, okay, well, from this picture here, you can take this and then stretch the neck. So you don't do anything with pseudo-holomorphic curves to start. And essentially what you do is you cut along this hypersurface, throw out everything below, and then you attach on a negative symplectization end. So you attach on an R minus across this hypersurface. And you can rig that, and you can put an almost complex structure on here so that it's in this R invariant region here. In the R invariant region, it's adapted the way sort of Richard described yesterday, and up sort of here, at least in a neighborhood of that CP1 at infinity, it's the standard complex structure here. And there's a consequence of that. Gromov sort of says, okay, well, if we fix some point on this sphere here, then we can and fix any other point, at least in a neighborhood here, then we can guarantee the existence of some pseudo-holomorphic curve which passes through those 2 points. It'll be a degree 1 embedded pseudo-holomorphic sphere. And so then you just say, okay, well, what happens when we drag this point down? And so then you say, oh, well, you get this family of pseudo-holomorphic curves. So this family that sort of falls down into the negative symplectization end. And then what you do, or then what you'd like to do, is say, okay, well, look, here's, once I'm into the symplectization region, I can see I have this minimum here, and I have this minimum here, and I have this minimum here, and this minimum here. And in this region here, everything's R translation invariant. So then the idea is to kind of say, okay, here will just be R cross M. And then since everything's translation invariant, I can just shift my curves up. So this curve here will sort of map it so that its minimum is like right here. And then this curve here, we sort of would normally have image down here, but then we shift it up. And maybe it looks something like this. And then we do the same with this. And then we get a bunch of curves here. sort of as such, sort of piling up all sort of in this region, but we have sort of a sequence of curves. And then there's an idea that sort of the natural thing to do is to try and pass to the limit. That is, can you pass to a subsequence, guarantee convergence in some sense, and then ask sort of what sort of object do you find in the limit? And it turns out that, well, if it's the case that this energy is uniformly bounded, as you consider these curves falling into the negative end, then the answer is yes, there's a compactness theorem. You apply that compactness theorem, you get a finite energy pseudo-holomorphic curve, and you find periodic orbits. However, it turns out that because we're in the framed Hamiltonian case, we don't have an energy bound. And we expect it to be the case that, we expect there to be cases where, in fact, we run this process and we absolutely do not have an energy bound. And we know that because there's this result by Ginzburg and Garel that says that there's, I think a C2 plus alpha embedded S3 sitting inside R4, which has no periodic orbits on it. So modulo some regularity, smoothness sort of concerns, there's no periodic orbits, which means if you were to run this idea, you wouldn't have energy bounds on your pseudo-holomorphic curve. So that means we're in this regime where we absolutely have to consider the case that our curves don't have energy bounds. And that kind of throws everything off the tracks, sort of all simultaneously. There's an enormous number of results that just kind of fall apart if you don't have energy bounds. So then I often like to, when I'm thinking about these problems, I often like to think, well, what's like the worst thing that could happen if we lose an energy bound? And maybe I can sort of say, because it's the case that I identified that this was something like the area in the image in some window, right? That also gives us at least a little intuition geometrically about what it means to lose energy bounds. It means that there's some slice, right? As we pass through our sequence, we can find these thickened slices and look at the area in this region and see that it must be blowing up. It must be doing something disastrous, right? Really, really bad. So then you say, okay, what's the worst possible thing that can happen? And then try to prove that can't actually happen. So let me draw a picture of what I felt was sort of the worst thing that could happen. So I want to draw this sequence here a little bit differently. So curves are falling into your negative end. You shift them up so they're all sort of at the same level, and you kind of look at each one individually, and you see, okay, well, what happens as you pass through the sequence? And so maybe the first one looks nice. It's just like a little disk, and you say, okay, that's not a problem. But maybe the next one sort of looks, right? Maybe like something like a double cover of a disk, but not quite a double cover. It's sort of pushed off itself a little bit. And then maybe the next one sort of, right, some sort of messier branch. And then you can imagine, okay, well, maybe this gets really bad, right, as you progress through your sequence. Somehow it's just getting messier and messier, and it's doing so at sort of the absolute minimum point, right, the minimum direction of symplectization. And if you think about this for a bit, you tinker with pseudo-holomorphic curves, you think like this can't be, right? And kind of why not? And it can't be because it turns out that your omega energy, so this quantity right here, for instance, so each one of these terms here evaluates pointwise non-negatively on complex lines. And in particular, when you look at your energy, this portion here adds up, right? And in particular, it turns out from your curves, you always know the following. For our curves coming from Gromov, this is always true. This quantity here is always true. And so you say, okay, but if it's the case that the energy is blowing up, that means this integral is blowing up, but this amount is bounded, then that means it has to be this part which is sort of blowing up. But if this part is blowing up, what area is this seeing? It's seeing sort of vertical area in some sense, right? You have sort of horizontal bits and vertical bits, right? And then you sort of interpolate between the two. But if you can't have too much horizontal, it must be the case that it's all vertical. But if it's all vertical and you're looking sort of near the minimum, right, it seems very strange that in this region that somehow you could kind of pick up a lot of area, but then it would suddenly kind of bottom out and not sort of go down any further, right? So this picture kind of drove me nuts for a while. until we proved the following, which is actually not so bad. This is not so difficult to prove. So let's see. Let's assume that you have a pseudo-holomorphic curve. And let's assume, let's also assume that 0 and R are regular values of the function A compose U. So U maps from your Riemann surface into R cross M, and then A just sort of strips off the first component. Also difference from standard Hofer-Wysotsky-Zander notation, but it worked better for the way I wanted to think about the pseudo-holomorphic curves. Right, and so then what you can do is you can define S0R to be equal to A compose U inverse of 0 to R. So the picture sort of erased it. So maybe you have some curve. Maybe it's got genus. You don't know, but we want to assume it sort of goes all the way up to the top and all the way down to the bottom, and we define sort of. Right, we define the domain. So maybe it's the case that you have some, maybe it's the case that your curve actually sort of extends much further, maybe plus and minus infinity, or maybe you've got boundary or whatever, who knows. But I just want to zoom in on sort of this region here. Right, just this portion. Good. And then there's a theorem that we prove, which says the following. The area with respect to the pullback metric of this domain is less than or equal to constant integral U star lambda A circ U inverse 0 plus E naught times E to the C R plus E naught. I know that's impossible to read. Plus E naught, where E naught is equal to the integral of U star omega over, say, the entirety of your surface. Or if you like, it also works just as well over your restricted domain. So what this says, if you can read it, so what this says is that if you have some pseudo-holomorphic curve, and you know a priori that, say, for instance, your omega energy is bounded by some number, right, whatever, and you know what the lambda integral is on, say, along the bottom component, then you can bound in fact, the area of this region, and in fact, the lambda integral along the top, in terms of you can bound the area in terms of the lambda integral along the bottom, plus together with the omega energy of sort of the portion of the curve that's in here, or the total omega energy, and this distance r, but that it grows exponentially in r. So this is this e to the c times r here. And I should say that c only depends on ambient geometry. Right? So it doesn't depend on the curve itself, for instance. It doesn't depend on the genus or anything along those lines, or the omega energy, for instance. But it does depend on things like the frame Hamiltonian structure and your choice of almost complex structure. Good. So now an exponential, so we call this like an exponential area bound, right? So the idea is you know the lambda integral here, you have sort of exponential growth in the area as you sort of move out. That seems terrible for lots of estimates. But it rules out this case. right? It tells you that near an absolute minimum of your curve, you have a bound on the amount of area in a neighborhood of it. And that's good. That's good because then you can run target local compactness. Let's see, write it over here. So target local Gromov compactness, this is a result I had from a while ago that basically says, if you have this almost Hermitian manifold and you've got a sequence of pseudo-holomorphic curves with say boundary on the boundary of the domain, and you have uniform area bounds and genus bounds, then by trimming your curves a little bit near the boundary, sort of you get rid of this junk here, you can pass to a subsequence and find an actual pseudo-holomorphic curve. And you can see that's good in this picture because we had this exponential area growth bound, and we know that sort of the lambda integral, if you go just below the minimum, is going to be 0, right? We then have area bounds. We now have area bounds on our curves, and we can pass to a subsequence and extract this small patch of pseudo-holomorphic curve. Then you can improve that with exhaustive Gromov compactness. And there the idea is that, well, instead of looking at sort of this slice of maybe from sort of 0 to 1, you look at sort of 0, 1, and the area is bounded. But suppose it's also the case that on the slices from 0 up to 2, the area is uniformly bounded. And then 0 to 3, the area is uniformly bounded, so forth and so on. Then in all of these cases, you can run sort of target local Gromov compactness on the smaller bits and then kind of patch them all together and get actually a limit curve that's in fact proper. Right? And so this guarantees a limit. Guarantees the existence of a limit pseudo-holomorphic curve. And there's a theorem then which says that the limit is feral, which actually requires work, and I also have to define what a feral curve is. So definition. So suppose you have a pseudo-holomorphic curve, and we suppose 3 conditions. Let's see, I want proper, and I'll just say pseudo-holomorphic. 2, the genus of sigma plus the number of connected components of sigma plus something called punct sigma has to be finite. And 3, the integral of u star omega is finite. This is our definition for feral. So right, what do I want to say here? Okay, so proper, just preimage of compact sets is compact. We know what pseudo-holomorphic means, and this is our omega energy here, which we expect to be, at least in the example that we're working on, we know is going to be bounded because our curves are all coming from degree 1 spheres in CP2. Genus we can easily make sense of, that's no problem. The number of connected components, you might sort of say in the limit, why should that be bounded? And it basically boils down to a modification of like a monotonicity lemma, right? If you have sort of many, many, many components, then in some sense each one of them has to pick up a threshold amount of omega energy, as it turns out. And so that's sort of impossible. And then there's this quantity called punct, which is supposed to be a generalization of punctures. There it's a little bit strange because usually when one studies pseudo-holomorphic curves, the standard thing to do is to demand that the domain, your domain Riemann surface, be conformally equivalent to a finitely punctured Riemann surface. But we don't make that assumption here. I just want to assume that it's some Riemann surface. A priori, it could be conformally equivalent to something which has, well, without this condition, it could have sort of infinitely many punctures. It also could be conformally equivalent to, for instance, the complex plane with some finite number of closed disks removed. Like a priori, that could be the case. Maybe it's the case that your ends of your pseudo-holomorphic curves, the conformal structure is such that it's just really bad, and it doesn't look like the neighborhood of a puncture. It looks like the neighborhood of a removed closed disk. And so as a consequence of all those sort of weird things, this notion of puncts is, well, it's a little bit technical. I don't want to go over it right now, but it basically controls the number of times your curve can kind of split as you move up. It can sort of split and then have something capped off however many times you want, but sort of split and not return, right, not connect back up again. You want to bound the number of times that can happen. And so we bound this. So in my definition, we bound it a priori, and then that's part of the thing that you have to prove when you pass to the limit and guarantee the existence of a Faro curve. So as a consequence of kind of understanding that some notion of a limit exists, and because we have some idea that sort of area, local area, has to blow up as we pass to a limit, there's kind of this question of like, how can that happen, right? And so I think this diagram kind of gives you some picture of what's going on. So maybe, in fact, so let's say just sort of right above the chalkboard up here, right? That's where the top half of CP2 is. And we're going to consider curves as they sort of fall down into this region. And I want to draw them sort of diagrammatically like this, right? So the idea is, you have some curve, and it's a cylinder maybe, and then it comes down to some minimum and has some local minimum. So that's how I want to draw that. And then the idea is that as you pass through that family, right, you can fall deeper, right? You can fall deeper into this negative end, right? And then these wobbles here are supposed to tell you that, like in this region here, my diagram, like the length of my curve here looks like it's getting longer, and so I want you to think of that as like my area locally is getting longer for my pseudo-holomorphic curve. And so you can fall down deeper, but it turns out to be the case right? It has to always be the case that sort of in a neighborhood of that minimum, your area has to stay bounded. But as you get further and further away from that minimum and further away from the top, your area can get very, very large. Draw one more. So that in some sense, the area, the local area is blowing up as your curves get very, very long, and it only is blowing up in some sense in the regions which are very far away from the top and very far away from the absolute bottom. That's sort of the only thing that can happen. And that's why you would expect to be able to sort of run a local compactness on each one of these things and get some sort of a limit, and you could sort of make it taller and taller and taller and taller. But it also means that at the end of the day, you end up with this curve, even if you imagine it only has one positive end, right? The area somehow is getting sort of unboundedly large as you move up to the top. Entirely possible. We expect this to happen, right? Go ahead. So now, if it were sort of a just world, finding this Faro curve would be enough to be sort of done and sort of establish the existence of the theorem, right? That there exists this closed invariant subset, or rather establish that you're hypersurface the flow and that's not minimal. But maybe it's not a just world because it's not enough. Because the main thing that you have to establish is that after you get to the limit, it's not difficult to show that in some sense the positive limit of your Faro curve is a closed invariant subset. That's sort of straightforward. You tinker with it sort of a little bit. It's not so difficult. The hard thing to do is to show that it's not the entire manifold. So I wanted to give some indication of why it's not the entire manifold. Yeah. So everything I've said up until this point holds in sort of arbitrary dimension. There's sort of no restrictions there. But now we need to make use of the intersection theory. So let's see how I want to do this. All right. I haven't done this part of the talk before, so we'll see how it goes. So what I want to imagine is this family of curves. So just this is R invariant. We don't have to care about the top. And as these curves are going to sort of fall down, right, fall down further and further and further. So I'm going to draw those like this. And then what I want to do is I want to draw, it's going to look like the exact same picture, but then we'll modify it so I think it gets interesting. Right? And what I want to do is, so I want to draw windows here. So this is like the window that I want you to kind of focus on. And then there's going to be another window. I want you to focus on this one. And then another window. Let's pretend this curve is modified so my picture doesn't get too cramped. Then I want you to focus on specific portions of the curve. So I should have done this sooner. That's all right. In this bottommost window, I want you to focus on this portion of the curve. And this portion. Looks like everything. In this case, in this bottom case, it is. But then it gets more interesting when we look here. I want you to focus on this, and I want you to focus on this. And then in this region here, I want you to focus on this, and I want you to focus on this. And then you can see that in this region here, I want you to focus here and here. Right? And the idea is that by focusing on these sort of minimum pieces, you can pass to a subsequence if you need, and guarantee, again, you can guarantee the existence of a pseudo-holomorphic curve. You can make it feral if you sort of extend this stuff. That's not that difficult. The other interesting thing is that we're also always paying attention to the portion of curve that comes from the absolute bottommost one. And what that means is that as we're sort of this tower, right? You have this family that sort of falls down for like fixed, almost complex structure, but you have this family that sort of falls down. And I want you to compare sort of the minimum of one to sort of the positive end of sort of the lowest curve. And what happens when you do that, everything's translation invariant, so you can shift it. And then you can pass to a subsequence where you have some nice patch of pseudo-holomorphic curve here. It's got nice area bounds. It comes down to a minimum in the symplectization direction. And then in some sense, you also understand what happens on these ends. You have to do a lot of analysis to understand the behavior of the end of a feral pseudo-holomorphic curve. And it turns out to be as nice as you could possibly want, other than the fact that you don't have an area bound, like this area bound. They turn out to actually be fairly reasonable. And you can even make sense of a limit of these things. And so in some sense, the limit, right, you kind of expect that it has to have infinite area in some sense, right? And it also ends up having to be, if this is like some interval here, right? It also has to be of the form interval cross, right? Some subset in M, which is closed and flow invariant. And now our primary concern is, well, is this set everything? Right? We have to show that that can't be the case. But then you sort of say, well, wait a second. Okay, suppose it is everything. Well, then it would have to intersect, this nice patch of pseudo-holomorphic curve all over the place. In particular, you could find at least one place where the two have to intersect transversely. But if those two intersect transversely, then we can back up in the subsequence and find some level where this patch of curve intersects this patch of curve. But then that means that this curve here, say, for instance, has to intersect this curve here. But because these curves come from Gromov, we only have a single intersection point between the two, and it's outside of the R invariant region, and that's a contradiction. And so therefore, this limit set, this really messy, terrible limit set that your ferrule end converges to can't be everything. And you can see that very strongly you need this transverse intersection to be able to pass from this limit case to knowing that sort of somewhere previously in the sequence you had an intersection. That's where it shows up. That's where dimension 4 shows up. Any questions about that? Yes. So, let me think. Yeah. So, yes, it's important for at least for the analysis that we do, the way we do it, that we have a genus bound. That's really important. So the question is, where does it show up? And so what you can kind of see is a potential problem here. Is suppose that you didn't have a genus bound. And so what that means is that as you have your curves, you can do kind of weird things, right? You have a right? So this is supposed to represent maybe you sort of come down to a minimum, right? We think about thickening this, or look at a boundary of a tubular neighborhood or something. So you have a curve with very high genus. The idea being the sort of genus runs off to infinity. This sort of the further out you get. And of course, what that means is it's also possible. So how also do you get sort of genus that looks like sort of locally, right, in the right places? It looks like you've got a standard node forming. Yeah. And so, but if you have so we like to think of I like to think of the standard node like this. But of course, in these cases, maybe the standard node looks more like this. Right? And if that's the case, and you pass to the limit, then you think, okay, I get some sort of double cover locally here. Right, some sort of double patch. Maybe it's sort of nodal because it's got a piece right here. But suppose it's the case that that interesting patch of pseudo-holomorphic curve here passes right through the node. I don't know, and then I back up on the sequence and there's sort of no intersection. Right, a priori. I mean, this is at least one place. There's another place which is, I said, that when you pass to the limit, you want to make sure that it's feral, but that you need to have a finite number of punctures. I'm also sort of slightly concerned if you allow infinite genus that you could end up with sort of infinite punctures. And then this sort of phenomena also sort of shows up. So what turns out to happen is, what happens is that we end up having, how does it work? In some sense, because it's the case that we have this genus bound, as you move up the end, your curves can't kind of split and close together that many times. It's sort of finite. Outside of a large set, maybe they split and a piece caps off. Then you have sort of a monotonicity theorem or an energy threshold which says that anytime you have something which caps off, you pick up a threshold amount of energy, so in fact that doesn't happen either. And so what that means is that outside some very large set, your curve is actually really nicely behaved. And then it's also the case, so then, let's see. So this happens as well. And then, let's see if I'm trying to remember, if I remember correctly, right, this genus bound also helps guarantee that you end up with sort of a uniform local, sort of something like a uniform connected local area bound. The connected component of a small patch near a target point in the image has bounded area. And you can only guarantee that as long as you don't have high branching. And high branching it always ends up implying a lot of topology, either too many sort of positive ends or too much genus. And so I have to rule that out. And by ruling that out, I guarantee this sort of local area bound as I run up, this connected local area bound as I run up. Sort of a sloppier answer than I would have liked to give, but I can improve on it later if you like. Any other questions at this point? So let me finish by saying just a couple of things here. So one, how about a question like, what's going on here? I mean, the problem, and it's really strange, I think, right, is that we're in this situation where the pseudo-holomorphic curves that we're sort of used to dealing with, we think of them, I mean, morally, they're a lot like meromorphic functions on a punctured plane in some sense, right? You've got nice control of the behavior of your curves near your punctures. You've got nice sort of area bounds. They seem to have these nice properties. And now it looks like we can find curves that do sort of really weird stuff. We have no energy bound. I mean, from complex variables, you know, we might think, well, if it's not meromorphic, it has to have like an essential singularity, and then it's all over the place. It's doing sort of really weird stuff. But somehow these curves end up being pretty useful. They're not completely terrible. They actually have a lot of nice properties. So in particular, you can show that outside of a large compact set, your curves have uniformly bounded curvature. Right? That means you can't have nodes forming, and you can't have like non-immersed points forming. And you can again show this sort of uniform area bound as you sort of move out. You know your omega energy is finite, and so as a consequence of these two things plus target local compactness, you can kind of guarantee that outside a large compact set, you know, your curve is everywhere immersed, and all your tangent planes, you've got curvature bounds, and all your tangent planes are becoming more and more and more and more vertical. And you think about this and you say, fantastic, I must have a finite energy curve, and you don't. Right? What happens is your curves sort of slowly get longer, like your level sets get longer and longer and longer and longer. And so, let's see. You might ask, so what's the most reasonable looking limit set for one of these curves if it's not a periodic orbit? And it turns out, I think, that the nicest case is sort of something like, I guess, right? The idea here being that you have some, really I think that the limit in some sense is, what I think is going to end up being the case, we're sort of working on it still, is that in some sense, this is a bit of a guess, the limit is, or sort of, let me call this the end limit of a ferrule curve is something like a cyclic word of hetero or homoclinic trajectories. Right? So the idea is that you've got sort of, you know, A1, A2, or maybe I'll say A, B, C. So we have this sort of cyclic word, and these are supposed to be heteroclinic trajectories. And then what you look at is the sort of the omega limit set of one and the alpha limit set of the previous, and you have some sort of common minimal set sort of in between the two. And that this is somehow supposed to be a generalized periodic orbit. And that what these curves are sort of asymptotic to. So without writing anything else, I guess I'll say that I think a fundamental question that we're sort of working on right now is, are these ferrule curves essential or not? Right, so we kind of expect pseudo-holomorphic curves to detect interesting topology in the loop space, you know, for instance. We expect them to sort of generate homology, say, for instance. And here we find these weird curves. And then the question is, well, are they essential or are they not essential? That is, can we make some sort of a perturbation, and will they all disappear for generic perturbation, or are some of these things going to persist? If some of them persist, then it seems to be the case that we would expect a generalized, you know, symplectic field theory or contact homology or embedded contact homology or something. We expect to be able to make a generalization. If no matter what, these ferrule curves always exist, and we expect them to detect topological features, then we expect to be able to build some sort of a homological or algebraic invariant out of whatever objects it is that they're detecting. On the other hand, if you can perturb them and they all go away, then the idea is, in some sense, that sort of generically then you expect to be able to run SFT or contact homology, embedded contact homology, just on generic framed Hamiltonian manifold. And either of these things I think would be really interesting to understand. Can we do this? Like, which case is it actually? And it seems to be a very subtle and interesting question. And I guess what I think is most interesting, I think, is that as terrible as these curves seem at first, and they seem really terrible, right? they end up having lots, unexpectedly, they have lots of nice properties over and over and over again. And that, to me, sort of says, okay, well, we've got to sort of study these things more. And there could be something very interesting here. Okay, so I'll stop there.